Hello again. Today we're going to look at the second part of the Coulomb's law lesson, which is the principle of superposition. Well, in the previous class we saw how we could determine the force that a Q sub 1 charge exerted on a Q sub 2 charge, and it was given by Coulomb's law. What happens if instead of having two single charges, we have a discrete distribution of charges? In that case, Coulomb's law is not enough. We have to apply the principle of superposition, which is what we are going to study in this class. Well, the principle of superposition tells us that in a system of charges at rest, the interaction between any two of them is the same whether the others are present or not. The total force that this system of charges will exert on the charge Q will be the vectorial sum of the forces due to each of the charges of the system. Well, if we take a generic charge Q sub I, the force that Q sub I exerts on the charge Q, as we will determine it by Coulomb's law, which we will multiply by K, by Q times Q sub I, divided by the distance between these two charges, and by the unitary U sub R sub I. The unitary U sub R sub I is the unit vector that goes from the charge Q sub I to the charge Q, and we will determine it. As we already know, by dividing the vector R sub I with origin at Q sub I and end at Q, split by its modulus. We will do this for charge Q sub 1, Q sub 2, for the n charges that we have. Once we have calculated these n forces, what we will do is to add them from 1 to n, and we will obtain the total force acting on the charge Q. Let's see an example. Well, Amanda has 2-point charges, the first of 2 nanocoulombs located at the origin of coordinates, and the second of -1 nanocoulomb located on the OI axis at a distance of 1 meter from the origin. You place a charge Q sub 0 of 1 nanocoulomb at the point 1 meter, that is at this point here, and you want to determine the value of the resultant force, the value of the force that these two exert on Q sub 0. What do we have to do? The first thing we have to do is, once we place the charges in the position where they are, we calculate the vectors R sub I sub 0. So let's do that. We calculate R sub 1 sub 0. The R vector sub 1 sub 0 will be 1 minus 0i. 1 minus 0j coordinates of the point where the charge Q sub 0 is located minus the coordinates of the point where the charge Q sub 1 is located. Its modulus, how much is it worth? Root of 2, so the unit vector will be R sub 1 sub 0 divided by its modulus, and therefore it is 1 divided root of 2i plus 1 divided root of 2j. We draw it. Next, what are we going to do? We'll do the same thing, but for the charge Q sub 2, that is, we'll determine R sub 2 sub 0. R sub 2 sub 0 will be 1 minus 0. And 1 minus 1, 0. Then the vector R sub 2 sub 0 is the vector I. Its modulus is worth 1, and therefore the unit vector will be the unit vector I. We draw it also and go on to calculate the forces on Q sub 0 due to the existence of Q sub 1, that is F sub 1 sub 0, and to the existence of Q sub 2, F sub 2 sub 0. We are going to calculate it as if the other one were not there. Then the first thing we do is take into account Coulomb's law, express Coulomb's law for that charge, and therefore now we will put how much is U sub R sub 1 sub 1 sub 0. How much is R sub 1 sub 0 as they come in this expression? We will take into account the values of Q sub 1, which is 2 nanocoulombs, which expressed in the international system is 2 times 10 raised to minus 9 coulombs. The value of Q sub 0, we will also take into account 1 nanocoulomb expressed in the international system will be 1 per 10 raised to minus 9 coulombs. And the value of K, which let us remember was 9 times 10 to the nearest 9. In the international system, Newton square meter square Coulomb. It should be noted that all units must be in the international system. Substituting values, we obtain the value of F sub 1 sub 0. As we see in the slide, we draw this force, and we would already have the force that appears on Q sub 0 due to the existence of Q sub 1. We need to calculate the force that the charge Q sub 2 exerts on Q sub 0. What are we going to do? We express Coulomb's law for such a charge in generic form. We take into account the values we had already determined for R sub 2 sub 0, and it's unitary. And then what do? We take into account the values of the charges and express them in the international system. Q sub 2 will be minus 1 per 10 raised to minus 9 coulombs, and Q sub 0 is 1 per 10 raised to minus 9 coulombs. We take into account again the value of K, and we substitute the values and obtain the value of F sub 2 sub 0, which is minus 9 times 10 to the minus 9, and we draw that force. The forces, as we are in the international system, will be given in Newton. Well, we need to determine the total force acting on the charge Q sub 0. And what do we have to do? Apply the principle of superposition, that is, add up vectorially these forces. The x component of this force plus the x component of this force with its corresponding sign, j component, and j component that it does not have. Well, adding up, we obtain that it is minus 2.64 times 10 raised to minus 9 and plus 6.36 times 10 raised to minus 9j. In Newton, we draw it, and we have the total force. If we want to determine the angle that this force makes, with the x-axis, what do we have to do? We will have to divide the force, the component. F sub I of the force divided by the x component in modulus. That tangent is worth 2.4, and the angle, therefore, is 67.5 degrees. If we wanted to determine the modulus of the force, what would we have to do? Well, we would have to take the square root of the sum of each of the components of the force, squared. We would finally get 6.88 times 10 raised to minus 9 newtons. In summary, what have we seen? We have seen the principle of superposition, and we have applied this principle to an example. We have determined the total force that appears on the charge Q sub 0 due to Q sub 1 and Q sub 2, that is, to a discrete distribution of charges. We have determined the angle that this force forms with the x-axis, and we have also determined its modulus. Well, that's all. See you in the next class.